And I'll start by just framing what I'm going to cover in the context of traditional IT infrastructure, which is the vast majority of today's IT infrastructure still on premises. The standard server with the standard storage network stacks that are running on the hosts, virtualized, ideally, that are talking to the hardware. In some cases, the hardware is directly attached to the virtual machines, but in many cases, there's compute that happens in the host. Now, if you take a look at the modern cloud architectures, it is focused on disaggregation, pulling that computing that is supporting those virtual machines, the storage and network aspects of computing, off onto an offload card. This accelerated offload card in Azure is called Azure Boost, and we announced it, I think it was last Ignite in Seattle, the first Azure Boost. Just to be clear, we've been disaggregating parts of our infrastructure for a decade. Our first network accelerated offload we released in 2014. And that was Azure Accelerated Networking, which gave us high throughput. It wasn't on a separate offload card, but it was offloaded into FPGAs, much like the offloads that we still have on Azure Boost with FPGAs. Here's a picture of today's Azure Boost card. I'm going to talk a little bit about what's going on inside of this in the next few minutes, but you can see a couple things there. There's two network adapters there. Those are Ethernet 200 gigabit ports, or 100 gigabit ports each, for a total of 200 gigabits coming off the card. That large block in the middle is the FPGA, and then the smaller block to the right of that are ARM cores running Linux. This is, in fact, it's Azure Linux running on those ARM cores. So I never thought I'd be saying that in 2014, that in 2024 I'd be saying Azure Linux is running on our offload card. But here we are. Now, we're using Azure Boost for a few things. One of them is to accelerate remote storage processing. So you can see here the before. We started offloading remote storage. You can see the traditional architecture, like I mentioned, virtual machines talking through SCSI, those storage packets, those blocks going off into the Azure software stack through Hyper-V and down to remote storage. With Azure Boost, the after picture looks very different. Now the virtual machines are talking through NVMe interfaces that are projected up from Azure Boost into the virtual machines, and that traffic is going through the accelerator off into the remote storage, whether it's an Ultra SSD disk or an Azure Premium SSD. One of the things that we get out of this architecture that we've developed with FPGAs is the ability to update it while the fleet is live. So rather than waiting for new revs of the hardware, we can actually optimize the acceleration code on the FPGA to bring higher speeds and feeds. And so just one example, when I announced Azure Boost last year, we supported 650,000 IOPS, cloud leading at the time, on 2 sockets. Today, now we support 750,000 IOPS on 16 sockets. And the 16-socket support we brought into the picture to support our M-series virtual machines, which some of you have seen me demonstrate, like running Task Manager on 1,700 cores. Those are the M-series. And then we've also been able to dynamically upgrade the throughput from 12.5 gigabytes per second to 14 gigabytes per second. We've also been using Azure Boost for local storage acceleration as well. Again, in the traditional architecture of IT infrastructure, you see the virtual machines talking SCSI through the virtualized stack down to the SSDs. Now what we're doing is using multifunction SSDs, projecting those SSDs right up into the virtual machines through Azure Boost, controlling the security of that connection, and that allows us for this very high throughput access for virtual machines to local storage. Again, by accelerating local storage, we've gone from 3.8 million IOPS support on a single large virtual machine, E-series virtual machine, to 6.6 million IOPS. It seemed like just yesterday that Jeff Woolsey, some of you might remember him, was showing, wow, 1 million IOPS on Azure Converged Infrastructure for Azure Stack HCI was back then. Here we are now talking about 6.6 million local storage IOPS on a commodity virtual machine in the public cloud. We've also gone from 17.2 gigabytes per second to 36 gigabytes per second, over doubling the amount of throughput now we offer on those local SSDs. And one of the benefits we get out of this comes in the context of live migrating virtual machines that have large amounts of local storage. One of the challenges we've traditionally had, because of the slow throughput we were getting off those SSDs, is the transfer times and the brownout times were extremely long, and the blackout times were extremely long if you had a very storage-intensive workload. So what I'm going to show you here is a demo of live migration of a very storage-intensive application. Now, this is not going to actually show the virtual machine live migrating. We're going to actually just live migrate the local storage, and you're going to see the blackout of the live migration. And then the virtual machine is just going to continue running on the local system, so you can see the performance continue afterward. So this is a little performance testing tool that's just going to drive TPC SQL queries. I'm going to go ahead and kick that off, and you can see it's driving about 1.8 million transactions per minute off of these local SSDs. I just kicked off a live migration, and then you can see a little blip as the live migration of that storage starts. This is the brownout period where you can see the throughput is dropped, and by the way, every one of those clicks is 10 seconds. This is just sped up so that we're not waiting while that entire SSD is being live migrated. And then we come to the end of the live migration where we've caught up with the virtual machine. There's a blackout you just saw, lost the RDP connection. Now we're back after the blackout, and we're back to normal processing. And here's perfmon showing the TP transactions per second. It's about 30K transactions per second. You can see the entire time reading it right up into the brownout, small blackout blip, and then we're back and running. So now we're able to live migrate even virtual machines with large amounts of local storage because of Azure Boost. We can do it very efficiently and get these low blackout times. So let me talk a little bit about what we're doing in networking. That's a look at storage, remote and local storage. Let's talk about Azure Boost and remote, so networking. One of the benefits we get out of Azure Boost and networking is, like I said, 200 gigabits per second because of Azure Boost's network adapter support, 400,000 connections per second. And then we've got now redundancy because we've got 2 links coming off the card. They're going to different links in the top-of-rack router, so now we have more resilience there, actually 2 routers. So now we can actually service a top-of-rack router. One fails, and we don't lose connectivity to those servers. But a big thing that we're getting out of this architecture of offload is better servicing times, where instead of when we want to service the network stack, we don't have to bring down the entire server, bring down the entire hypervisor, and cause this big blackout, or even reboot the virtual machines. Now we can do it very quickly on the Boost offload card. The way that network driver updates happen in Boost now is that on Boost, there's a network agent there that is managing the flow states coming off the virtual machines. When we bring up a new network agent, and get it, well, so the old network agent leaves its virtual flow states in memory, in RAM, on the Azure Boost card, shuts down, the new one starts up, and there's a handoff of state. And that means there's no copying of state, there's no serializing of state. It's basically in-memory transfer of all that state. And this is actually what we're going towards, a journey that we started with something called Virtual Machine Preserving Host Update that I talked about close to 10 years ago. We've been evolving our update infrastructure, even into Azure Boost, of doing this memory transfer so you never have to serialize or deserialize when you're updating components of the operating system. We can do this not just with the network agent, we can do this with the entire network stack processing on Azure Boost as well. The blackout times vary, depending, or the brownout times and blackout times vary. But what I'm going to show you here, a quick update, is actually a demo of updating the network agent on that Azure Boost card. So here, I'm going to run a little benchmark tool that just is showing number of connections per second, and this is where we're going to see the effect of that network update. Here's the version of the agent that's currently installed. Now update to the new agent, so this little script does that. And you can see that there's really no impact on that throughput there on the left side. Now I take a look at the new version of the agent. We can see the new agent is now up and running. Now, how much impact did that have on network capability for the virtual machine? Well, there's 2 aspects of it, gray out time and blackout time. And the gray out time is about 100 milliseconds. The blackout time is about 250 milliseconds. Gray out means, it's the term we came up with to mean that the network isn't supporting new network connections, but it is still processing the existing flows, versus blackout time means the whole network traffic has stopped. But you can see 250 milliseconds now while we're doing a full update of our network stack, which is basically invisible to the vast majority of applications. And so now we can service our fleet much more efficiently, bringing new capabilities like the ones I showed you, improving throughput and connections per second on the networking stack, while the virtual machines continue running happily along.